we use like dummies, right? So we turned the categorical into quantitative, and then we could do regression. Cool. And over here, when we had categorical variables that we're trying to predict, what was this problem called? So we looked at a tool for doing that. So logistic regression was the specific technique we looked at, and it was part of a broader group of algorithms solving a particular problem. I may not have said it out right. This is classification. And again, these probably go down to both columns, but the techniques we've looked at so far work best for quantitative inputs. So when we have to deal with more categorical inputs, we'll use different techniques. Okay, so the technique we looked at on Thursday was logistic regression. So let's kind of just do a quick recap of that. So what was the sort of key idea behind logistic regression? So we're fitting basically this S-curve, the logistic function, to our data. Right? So if our data looks like this, so we're fitting a curve that looks something like that. And what does this curve tell us? So when I use it for prediction, what does it tell me?
There's a significant cutoff point.
So I am interested in this cutoff point at about, what value would that cutoff point be? 0.5. And so what is the value of the curve tell me? Tells me, so I think, I'm not a statistician, but I think likelihood has a precise, slightly different meaning that is related to probability. So this is going to be the probability that our data is in a particular class. And so if I predict here, my curve tells me that there's like a 25% chance that an input at this spot is in this the top class. Cool. And so the parameters, the formula of this, basically we're fitting so P of we call it P of X. This is the formula that we're actually fitting. Okay. So the logistic function is an S-curve with that goes through 50% at 0, I guess. And to make it fit our data, right, we basically fit a line and then smush it with our S-curve, and we can adjust the slope and the intercept of the line to change where I cross the 50-50 threshold and how steep, how quickly I transition from predicting 0 to predicting 1. Okay, so everybody kind of remember that? I think we also saw an example with the graduate admissions problem, where the function we actually fit was a logistic function of multiple variables. So here we have multiple inputs. So we're no longer fitting a line and then smushing it. Does anybody remember by multiple variables, what shape do I get when I have like all 3 of these linear terms? I've added another dimension. I no longer am fitting a line shape. What's the shape that I'm working with now? plane. Right? So I'm taking a plane, and then I'm smushing the plane into the sigmoid, the logistic function curve. Okay? So I may have a sheet of paper. So what I'm going to get out of this, in my however many dimensions I have, I'm going to fit this plane in my data, and then I'm going to curve the whole plane. Okay. So what is going to be the shape of my cutoff? Like if I looked down from the ceiling, the floor contains my GPA and GRE. If I'm looking down, kind of at this, what's the shape of my like 50% cutoff line going to look like? I just gave it away. What's the shape of the 50%? It's going to be a straight line, right? Because I can rotate this, right? But I'm always bending like in one direction, so I always have a straight line cutting off between my data. Does that kind of make sense? So we'll see an example of where that is important in a little bit. But that's the key idea, is when this division, right, I'm fitting this curved surface, but my classification is still like a linear thing. I'm still like trying to draw a straight line between my yeses and my nos. Does that kind of make sense? Okay. So that's what we talked about Thursday. Any questions about that? That was logistic regression. So we saw a couple of examples where logistic regression doesn't work that great. So one problem was when there were multiple classes, or more than two classes. And so this was great for predicting yes or no, but it wasn't so great at predicting red, green, or blue, right? Because there's only, we go from 0 to 1. How do we deal with a third option? Okay. And then the other another problem we saw is if my data looked like this. Okay. I can fit a logistic regression curve to this data, but it's not going to describe the data very well, right? So I could fit one that looks like this, and I'm going to misclassify all this stuff here. More likely what's going to happen is I'm going to fit one that looks like this, and I'm just going to classify everything as a 0, and these ones up here will basically just get ignored. Okay. So the logistic regression assumes that there's like a transition point where you go from one class to the other, right? And if the shape of your data doesn't look like that, then that's not going to work that well. Cool. Right. So today we're going to talk about another technique for classification. Okay? That is conceptually extremely simple. There's no calculus, very little math, and it can work quite well. And this is called K nearest neighbors. Do you have a question? Or? No. Okay. And from the name of this technique, you could probably guess what the algorithm is. Anybody want to take a stab at it? So the neighbors are nearby points. We grab k of them, and how are we going to use that to classify the point we're trying to predict at? So we know the distance between them. So let's say I'm interested in a point here. So my nearest neighbors might be these points. So these are my k nearest neighbors. And how am I going to use these to predict the value of my glue point? Well, so if I did a fraction, I'd be like down here or something. Voting.
Just like what's more likely, like there's more neighbors up there, so it's more likely that'll be up there.
Yeah, so basically the simplest thing is we just vote, and majority rules. Okay. So that's basically k nearest neighbors. We find the points nearby where we want to predict. We vote, so each of them votes with whatever class they're in, and then we just count them up, and we predict basically whichever there are more of nearby. So that's k nearest neighbors. A very simple idea. We just pull the nearby group and vote. So the kind of tricky part that we need to decide on is what should our k be. So what are the kind of very extreme values we could pick for k? And then we'll talk about kind of the pros and cons. So what are the craziest values of k I could pick? I could pick all of the points. 0 might not be that useful, but 1 would be interesting. Okay. So what happens if I pick k equals 1? What happens if I pick k equals infinity? So if I pick k equals 0, basically I guess I'm just guessing. So, all right. So let's think about k equals infinity. What are my predictions going to look like if I pick k equals infinity? So wherever I want to predict, let's say I want to predict right here. What do I do? So I add up all the other points. I vote. Right, in this case, who's going to win the votes? The bottom would win here. Okay. Does it matter where I'm predicting? No, right? I'm looking at all of the points all the time, right? So no matter where I predict, I will always get the same answer. Okay? So this is a very smooth classifier. Right? There's not going to be a lot of variation, because there will be 0 variation, because I will always predict the same class for everything. So my prediction with k equals infinity would look like that, right? Because I happen to have more 0s than 1s total, so the 0s win the votes every single time. All right. I'm going to change up my data a little bit for the other case. So let's just, what would happen if I picked k equals 1? So one extreme is k equals infinity. I just do a single majority rule vote. There's no variation. I do k equals 1. I ask just the nearest. So if I drew this prediction line, it would look something like that. Is this a good predictor? Probably not. Right. So what sin did I commit here? Overfitting. Right. So if my k is too small, I overfit because any kind of outlier or unusual data point is going to cause a big, shift in my predictions around it, right? And so that's no good either. So if I picked, in this case, like k equals 3 or something, then I'm going to get, the prediction that I wanted. It's going to kind of ignore the outliers and give me the result I expect. Okay. So some nice features about k nearest neighbors. It's a non-parametric method, meaning there's no particular input shape I'm trying to fit. It just fits whatever data I have. And so that's kind of a pro and a con. If the kind of shape I expect is either difficult to specify or I don't know it, this is really good because I don't have to like have any background expectation of what's going to be there. But it also means it's kind of hard to summarize, right? I can't. I get this output, I get this classifier I can use to look up new points, but I don't have like a nice formula to plug in. Okay, so I'm kind of trading off like a nice mathematical compactness for expressivity, right? I can describe more complicated data, but it takes, I need to do a prediction. I kind of need to store all of my input points. Another nice thing about this, there's basically one knob to tune, and it's very intuitive, right? Which is k, right? So I can adjust the number of neighbors, and as I shrink k, I know I'm going to get a closer fit to my data, but more noise. And as I increase k, I'm going to get smoother results, but I'm going to kind of blur my boundaries more. Okay. There's some other sort of tweaks you might consider. So, so this kind of the simplest voting you could do is just 1 point, 1 vote, majority rules. Okay. But you could also consider like doing some sort of weighted voting. So like nearby points cast, get more ballots. That's kind of like adjusting k, and it can smooth, help you get like sharper boundaries, stuff like that. So you could kind of tweak this general idea a little bit in how you actually do the voting, if you wanted to. I would say if you have kind of enough data and it's dense enough, it probably doesn't matter all that much exactly how you vote. You're going to get more or less the same results. But if your data is sparser, then maybe you want to do a more complicated like voting scheme to kind of take into account that there might be big distances between points. Right. So that's k-nearest neighbors. It's like probably the simplest conceptual technique we'll talk about all semester. Any questions about the key ideas, how it works, what it's supposed to do for us? Okay. So somebody had a question last year as I was teaching about this, which prompted either the next or the one in the future assignment and the rest of the lectures for this week, which is about how do we actually implement something like this. Let's say I want to do, I'm just doing k equals 1, and I have this huge data set. I have millions of data points, okay? And I want to do just k equals 1, k nearest neighbors fitting. Okay? How would you implement that? Right. So when I want to predict a new input point, right, I give you the coordinates of that point. What do we have to compute in order to do that prediction? Yeah, so if with k equals 1, it's not even points, it's just I have to find the closest point in my input data set. Okay. And I just have to look up the class at that point and return it. Okay. So how do we do that efficiently? So yeah, so let's say I have 1D data. So I have something that looks like this or this picture, right? I can find that point quickly by if my data is sorted. Right? So if my data is sorted, what do I do to find it? What's the algorithm I'd want to use?
Like a binary search.
Binary search, right? So let's say I have 1D data, right? So when I pre-process, right, I could sort, and my prediction might be binary search. Okay. And so my pre-processing, what's the cost of that going to be?
And log in.
Maybe n log n, and my prediction,
Log in.
log n. Okay. If I do k nearest neighbors, so where k is not 1, right, my pre-processing was not going to change, right? My search, how would that change? Kn log n. So if kn log n, or sorry, k log n, would imply that I have to do basically k binary searches. Is that actually what I have to do? How would I find the k nearest neighbors in a sorted list? So I would use log n to find the closest point. And then how would I find the k nearest neighbors? Yeah, so I'm going to spread out, right? I'm going to go like left to right. I'm going to like try to, get the closest one on the left side or right side. I go out. And so the real cost would be basically log n to find kind of the middle of my range. And then depending on what k is, I'm just going to go like kind of one at a time out. So this would be like a log n plus k kind of deal. So we can see that actually the larger my k, I'm going to have sort of a smoother fit, but also a higher query cost. Right? So usually n is way, way, way bigger than k, right? I have millions of data points. My k might be 10 or 100, something like that. So this k is probably small relative to the other costs. But as intuitively, it makes sense. As I want to ask more voters, right, it takes me longer to find them. To do that. So yeah, 1D data, cool, I sort it. Not a big deal. What do I do about 2D data? Now, my data looks like this. How do I deal with that?
Could you create an adjacency list? Like use your X points as essentially an array and then maybe like a BST for your Y?
So what am I storing here?
Essentially an array of BSTs.
An array of BSTs, and what is the array indexed on?
it would be your, I guess your root node would be the x-axis.
So I would have one BST for each x point. Well, if I do that, then probably there's only one. The BSTs are probably all going to be size 1. And so x is a continuous thing. It's unlikely that I'll have 2 points that have exactly the same x value. I think that's a start for a good idea. How could we tweak that slightly to maybe make it a little more practical? So instead of having a BST for each x coordinate,
Or like a bin.
yeah, bin. So one thing we could like split. Could split into little strips and then make a BST in each strip based on the other coordinate. So this is an example of the general strategy we're going to use. This is an example of a spatial partitioning data structure where we split our space into various regions and we order them so that we can do searching. So we're going to talk about a whole bunch of these data structures. You're going to implement 3 of them for an assignment coming up. So this would be actually kind of a hybrid of 2 of the data structures we're going to talk about. So 2 of the kind of key strategies we'll use are binning. So we'll split stuff up into like kind of boxes. And then the other thing we'll use is something like a binary search tree. So yeah, this is kind of a hybrid of 2 of the main techniques we're going to use. Yeah.
So that's like it has an X and a Y.
Yep.
No Z.
No Z in this picture, but real data might have way more dimensions. So having a data structure that works in an arbitrary number of dimensions is a good idea. So yeah, we'll look at a few different data structures and see how they perform in a bunch of different scenarios. So this is kind of how we're going to do KNN. We need to somehow figure out how we can store all of our input points so that we can do fast searches to get neighborhoods. And also we don't want the pre-processing time to be too high. So that's what we'll spend the next couple of days talking about. Yeah?
Would you be able to still sort it like the first way, but just based on the X value, kind of like you would on a chart? You have points laid out on X and then search by the X.
Yeah, so I could sort based on the x-axis. The issue there is that so let me give you an example of something that's bad. So if my y's are really small here, if I'm searching for a point, for the neighbors of a point up here, the points that I want actually might have an x value really far away from its x value. So it's closer to go along the x-axis than for me to find the points in the same kind of x bin. So that's something we have to take account of when we design these data structures. So yeah, this is a hard problem. It's part of a field called Computational Geometry, which is it's a really fascinating, it's a mix between kind of geometry and algorithm design. So there's a lot of these like kind of really simple sounding kind of geometric questions that you want to ask. And the making sure that you always get the right answer as efficiently as possible, coming up with those algorithms is really, really hard. So it's really interesting field of theoretical computer science, and we'll just kind of scratch the surface a little bit. Cool. Other questions? All right. Let's take a look at a little bit of code. So we'll look a little bit at logistic regression on a new data set, and we'll see kind of where it breaks down. And then we'll see how KNN is more effective for this particular data set. So yeah, we're going to look at a new data set called the Two Moons data set. And basically it's there's two different types of moon or something, and there's two different independent variables. I don't know where the name moons comes from, but so this is what the data looks like. So there's these two different types of data. You can see there's kind of two different groups, right? There's some overlap here. There's a little bit of noise at the boundary. So yeah, this comes from this make moons function that comes from scikit-learn or something. Oh, here. Scikit-learn data sets, so it has, and so you can make as many of these moons as you want. It's got some sort of random seed. Yeah, so this is, here we're just, we're making some moons. So the x's contain the coordinates of the moon, and the y contains whether it's a 1 or a 0, blue or red. So here we're plotting the class 1s as blue, the class 2s as red. And so this is what that looks like. Yep. So our first stab at a classifier, we'll try logistic regression on it. So we're gonna, so the logistic regression, this time we're using the scikit-learn version instead of the stats models version. Again, it looks a little bit different, but the ideas are the same. So basically for this one, we just give it the x's and y's and say fit. And we will plot our points again. And then here what we're doing, we'll take a closer look at this line here, but what we're doing is we're plotting the regions where we will classify blue or red and the dividing line. So we're going to basically draw our classifier on top of our data. And then we'll look at that. So yeah. So this is what our logistic regression comes up with. It kind of works. Right? It gets kind of the bulk correct. But I think you'd agree, like this area in here and this area up here, like we're getting a straight line dividing them, but it really isn't a straight line that separates them. Does that kind of make sense? Like it's not the division between the blue and the red, at least visually, does not seem to be a straight line. There's kind of some of the techniques we'll look at are really cool. They fit straight lines to everything, and then what they do is they basically warp the world so that when if you imagine these points on a piece of paper, they like kind of twist the paper so that if you draw a straight line across it, it works well. So we'll see some techniques where when we actually draw the line, it'll look curved, but it's kind of like we drew it on a curved, on the twisted sheet of paper, on like a sheet of rubber, and then let the rubber go back to the original. So we'll see some techniques to do that. So that's another way of getting around this problem of like, hey, these lines aren't really straight. You like kind of twist the world until a straight line works. So those are pretty interesting techniques. But we're not going to do that here. So another way of looking at what's going on here, so we'll just look at what the functions we use to plot this. So we're plotting two things. So these two functions we're looking at, contour F is contour fill. Okay. So how many people have gone hiking and used a contour map? So what does a contour map show you? Shows you the elevation, and how does it show you? It's not a 3D thing. So what does a contour line show you? So it shows you all the points on a that are the same elevation, right? So that's what a contour plot shows you. It is a 2D plot of 3D data, essentially, or it could be more dimensions, but we'll look at, we have basically 3D data. We have X, Y, and then we have a Z, which is our probability. Okay. So the contour fill is going to, instead of drawing like lines at different heights, it's going to just color map. So it'll color code the height at each point. And then the contour is going to draw lines. Okay. So what we're going to do here is we're going to draw contour lines, and this is going to draw the shades. Okay. Right. So the way that we actually do this is we make up a grid of all of the X's and Y's. So we have to basically sample like all of the little points in our image, so all the pixels more or less. Okay. So that's what these this mesh grid takes a range of X's. So like when we would plot a normal curve, we'd make a bunch of X points close together and then compute the Y's of all those and plot them. So here we're making a bunch of X's, a bunch of Y's, and then the mesh grid makes pairs of all of them, so we get a whole grid full of basically X, Y coordinates. And then we are going to predict what the classifier says at each one of those points. Okay. And then we will draw the contours based on the X, Y, and position. Okay. Most of this here is like kind of noise related to just getting the dimensions of the matrices right. So like whether the X and Y's are separate columns or like a different dimension in our data or all that stuff. So that's what kind of all this noise here is just about, like shaping the blocks of data so that they work right. So yeah, we see here the contour line that we get, where the probability is 0.5, is this straight line, and that doesn't really match our data. Another way of looking at this is instead of using a contour plot, is a 3D plot. Okay. This angle is not all that useful, so I'm going to uncomment this magic line. And this is actually going to turn all of my plots into interactive things. It makes everything extremely obnoxious and slow. So I'm going to just turn it on for this, and then we'll reset it. But yeah, see how obnoxious it makes the other graph. And if we plot this one, we actually get this cool rotatable 3D thing. And we can see we're actually, it's like that sheet of paper, we're finding like where the sheet of paper folds up. But again, it looks like this sheet of paper, which is why we get that line. And this seems to be a pretty sharp division, so the classifier is pretty confident about where we cross over from blue to red. Does that kind of help make sense of what the logistic regression is doing a little bit? So this is just that the sheet of paper has been folded. The contour graph that we were looking at is basically we're just plotting this line along the 0.5. All right, so I'm going to turn off the obnoxious bits. And so if we look at the confusion matrix, we'll see that our accuracy is okay, but it definitely looks like we could, if we had chosen a better classifier, if our decision line had looked differently, like we could have done better. Right? Does everybody kind of agree about that? Okay. This isn't like, so for the GRE, GPA thing, when we looked at the data, it was like, didn't look like any decision that we made would be good, right? There was no separation between the data points. It was all kind of mixed together. But here, like, yeah, it seems like we could do better. Okay. So we'll look at KNN. And so we'll start, we'll look at this, this data set called the iris data set. So this is measurements of a bunch of flowers. And there are 3 species of iris, and we have measurements for their petals and their sepals. And the sepal is different from a petal somehow, but I don't really understand the difference. Okay, so it's we're measuring different parts of the flower, and we're trying to predict this species based on it. So yeah, this is an old data set, 1936. We have these 3 species of iris. We'll take a look at Seaborn is like this library built on top of Matplotlib that draws prettier pictures by default. So this is like the scatter matrix, but it looks nice. Okay. So we are loading the iris data set, and then just doing this pair plot. So it looks like we should be able to classify these if we look at kind of the right data, or we look at the right dimensions of the data. So it looks like basically no matter what we pick, it's going to be really easy to tell the setosas apart from the others. Like the blue ones are pretty separate. To tell the reds and the greens apart, we kind of have to be careful about which dimensions of the data we look at, right? If we picked the sepal width and the sepal length, right, it looks like the greens and reds are mixed together, so we're going to have a tough time classifying them here. But if we looked at petal length and petal width, then that's going to tell us more. So this is the data we're working with. So we're just going to look at the first 2 dimensions. So these will be I think the sepal length and sepal width. We'll see that yeah, it's going to be hard to tell everything apart. So we're just going to scatter plot based on those first 2 dimensions, and this is the data we're going to work with. Okay. So we're kind of limiting ourselves if we only look at these 2 dimensions, but we should definitely be able to tell this class apart from the other 2. So logistic regression is going to be tough. It's going to be tricky because we have 3 classes. If we were just interested in the red versus the blue-green, do we think logistic regression would work well here? I think it would. What would give you that confidence? So they're separated. So that's good. Right, that means some classifier would do a good job. What about the way this data is laid out makes it look like a good candidate for logistic regression? So how is logistic regression going to split this data? Like geometrically, what's it going to do? How is it going to divide the data? So it's going to fit the logistic function. If I kind of look down at where the dividing line is, the shape of the dividing line, right? It's going to be a straight line across my two coordinates. And here it looks like a straight line would separate them pretty well, right? So I think logistic regression would actually work pretty here. I can draw a line between a straight line between them. So if I wanted to try logistic regression to tell the reds from everything else, then I think that would probably work pretty well. Okay. But instead, we're going to use K and N. So we're going to do. So we're going to make this K and N classifier. The fitting here probably does something like sort the points or store them in a spatial partitioning data structure. And then we'll do the same. We'll do the same plotting thing. Okay. And then we'll draw the points. Okay. So this is with K equals 100. And it looks like it worked reasonably well. Not perfect, but it gets kind of the gist of it. If we look at the kind of the numerical score, we see that we did a really good job of telling the reds apart from everything else, and a not so great job telling the blues from the greens. So it looks like there's only one red that was misclassified. Or sorry, it looks like one blue was classified as red. None of the reds were misclassified, so everything we predicted that was going to be red was actually red. So all the red dots are here. So accuracy of 0.72. This is with K equals 100. That's a really big K. Let's maybe pull that down to like 10, see what we get. So with the K that's pretty small, what happened here? This is like some overfitting, right? This looks pretty weird to me. Okay. But, given that the data is weird, maybe it's a little harder to say. Accuracy went up a little bit. Okay. So maybe let's try to find a nice happy medium. That looks maybe a little bit better. Accuracy went down. How can we tell if we're overfitting or underfitting? How can we evaluate that? We could look at the smoothness. That's kind of hard to, that's a hard thing to compute probably. It's like an easier way we can decide whether or not our model is too complex or not complicated enough. We talked about this last week with regression problems, the least square stuff. We're deciding between a bunch of different models. We looked at the R square and the p-values and stuff. We don't really have that here. What was the other technique we used? Nobody remembers? Well, this is an important concept, cross-validation. Right? So what did cross-validation do? So we fit to some data, we test with other data, right? And we look at the accuracies of both, right? If they both have really low accuracy, what does that probably mean? So I'm doing really bad on my training data and my testing data. So that probably means I'm underfitting. It means my model is too simple. Okay. In this case, it probably means my K is too high. Right? If my K is really big, right, and that's like, imagine K is infinity, that's like the simplest model where I just say like, you know, all of my predictions are blue. Okay. So that's underfitting. I do bad in the training set and the testing set. If I do really well on the training set, but not so great on the testing set, what does that mean? Overfitting, right? So it means probably my K is too small, right? I'm looking too tightly at my samples, right? So if I have K equals 1, what is my training accuracy going to be? It's going to be the highest accuracy. It's going to be perfect, right? If my K equals 1, when I do a prediction on my training data, the closest neighbor is going to be that training point itself. So I'm going to get those right every single time. Right? And basically, it's like for my training data, I'm looking up the data that is at that point. Okay. But my testing data is probably going to be really bad because it's going to be super noisy. Okay. So if I want my training and testing accuracy to be comparable, and that's where I know that my K is. I've dialed in on about the right K. Compared to some of the parameters, the K is like, it's not super sensitive. So like, if I go from 10 to 11, it's probably not going to like wreck my accuracy or anything like that. But I want to I would kind of like binary search in on getting the right range. Okay. So let's look at the Moon's data set. So here we're doing KNN with 10. And you see that actually the line can curve to capture the data. Okay, so KNN is a more powerful model. It gives us more sort of, it allows the decision boundary to wiggle and curve, and so we can improve our accuracy. So in this one, our accuracy was 86. Look up here. Accuracy was also 86. I am using a different data set, so that could be, oh yeah. I'm not sure what changed there, but so yeah, I did improve my accuracy. Okay. So this allows me to curve call this the decision boundary, this like 0.5 probability line. So KNN lets it curve and wiggle. And in fact, it doesn't even have to be a curve. I don't know if you can see in here. I think there's little loops in here. So this is a little loop. So I have a little island of predicting blue in the red half of the thing. Probably that's not, probably for this data set, really you don't want that, right? If you have all these little like islands across, probably that means you're overfitting, but not always, right? Maybe your data is yin-yang shaped, and you need to have a curve between them, and you also need pockets of the other ones on the other side. Okay. So to make sure that we're actually hitting the right K, we can look at cross validation. So here's kind of what the cross-validation can show us for classification problems. So here, if my model is too simple, right, I'm going to have low accuracy on both the training and the testing data. If I'm, nailing it, the accuracy is going to be comparable. The test data is probably going to be a little bit lower, but it'll be pretty close. And if I overfit, my test accuracy is perfect. Right? I got every single one classified correctly, and my training accuracy is going to be really bad because that's not really what the data looks like. Okay, so I have underfitting, sweet spot, overfitting. And this is what kind of the error looks like for the training and testing data. So the testing data is usually going to be higher error, right? But it's going to be, it's going to like start going back up once I start overfitting. That kind of makes sense. So we're going to look here as we're going to kind of give you the punchline. So we're going to look at a bunch of different Ks and look and see how things, how the accuracy changes as we go through the different Ks. So, so we'll just have a couple of helper functions here. So here we're just trying to find the range of X and Ys for our various for all the various data sets. The decision boundary, we're going to use our model to predict. So we're going to give it the grid of points. We're just going to predict the class each point. To plot this, we're going to use the two contour plots. So we're going to do the color one and the line one, so we can see the decision boundary. Plot the actual points. We're going to predict the errors. So the accuracy score will tell us basically, how many we classified correctly and incorrectly. Here we're going to just draw on the plots the text value of the error. And here we're going to pick a bunch of different numbers of neighbors. And we're going to fit the data sets. We're going to plot all this stuff. And then we're going to put it all in one graph. So here, we're going to try with 200, 100, 50, 25, 10, and 1. And if you look at the output, it looks just like the simplified graphic we saw. Here we're underfitting. Right, our model is too simple. Our K is too big. Right, so we just get this kind of like simple line. It doesn't capture what's going on over here at all. Training and test accuracy are pretty low. Right, so training accuracy higher than a test accuracy, which is what we expect, but our training accuracy is not that good. Right. As we decrease the number of neighbors, we make the model more complicated. The line gets wigglier. And as we do this, our training accuracy goes up and up and up. When K equals 1, perfect, right? Every single training point is classified correctly because basically for every training point, we're just asking what is the value at that training point? And it turns out that that matches the value of the training point. So we get perfect accuracy. But our testing accuracy, it goes up for a little while and then it starts to go back down. Okay? Once we start to overfit. Right, so the line gets wigglier, and as we overfit, we have all these weird little islands in here and weird little bumps. That's not what the data actually looks like, so we've overfit at that point. So which one of these do we think is probably the best model? So this one looks pretty good to me. The curve is not super wiggly. It matches, like it's not a simple shape, but it's not like really, really high frequency. Right? So Wei said like if we looked at the curvature, this one is like much nicer than that one. And if we look at the accuracy scores, they kind of back us up that this is the best best test accuracy one. So this is probably the right model here. Okay. So yeah, that's KNN. It's really simple conceptually. Right, we just look at what's nearby and ask them to vote. As we tune the knob for K, as we make K really big, we get a really simple model. As we make K really small, we get a really sensitive model. When we have the appropriate number of neighbors, right, our training and testing accuracy are about the same. Right, we get a decision boundary that matches the data but doesn't overfit. That's kind of what we're looking for. So just to let's see what this looks like kind of around that sweet spot and see how sensitive things are. So we decided that 25 was pretty good. Let's kind of look at, so around 25. I expect that 20 and 30 are going to be pretty close to as good as the 25. So you can see these all look pretty similar. The accuracies are all very close. The sensitivity of the K parameter is not super high, especially if you have a lot of data. Okay, so that's a nice thing, right? You don't have to spend a lot of time adjusting your K, right? It doesn't matter that much as long as you're in kind of the right range. Any other questions about this? Okay. So to finish up, let's take like 10 minutes, and with the people around you, let's try to design a data structure that will allow you to do these neighbor lookups fast. Okay. So the challenge is we have a bunch of input points, okay? And for a new point, we want to basically find the nearest points. And so basically, we input is the point array. This is big, and then so this is kind of like our constructor parameter or whatever, right? And then we want to support this function, where given a point and the number of neighbors that we want to efficiently get back, an array of these closest points. So take a few minutes with your neighbors. Talk about what data structures you could design that would do this. Maybe start with the least efficient and simplest, and then we can go from there. Okay. So we'll spend a few minutes chatting in groups, and then we'll talk together about what ideas people came up with, and then tomorrow we'll talk about some common data structures for solving these problems.
So
Oh, okay. I can see that. Now, are you doing this work before now, or do you just data like this?
So we're returning and pointing, right? Right.
The only problem I can see with that is like, it's all over. And how much you can see when you're comparing those. So I feel like you need some sort of.
So we're just trying to so data sets.
Oh, you mean like yeah. I think we have yeah, and that's what we're can you use that that you showed above to summarize? Yeah. How much you could use super large basic for it, just like this one, or you can do 100. It seems like, yeah, that's
Structure. We got these points on the edge of the and we got other points.
yeah. So we did almost play with those hybrids, right? You would almost have a user define
So that one doesn't do so great when things are clumped. So then you think about how you like so it works really great if things are like distributed everywhere. But if you have like kind of clumps, so if you have like a Gaussian where all the systems kind of what works so well. Think about how you like
Even though the user subsidize them.
yeah. So or maybe what if you said you had so the problem would be if we did that like these are all the same, but now we have like 10 data sets instead of 10 blocks instead of just
so sorting by X and
grabbing a
Yeah.
yeah. The other problem is out here, like let's say this program, we have a bunch that are just like now
so that that would be kind of the simplest way. So the probably like your pre-process is nothing.
yeah, so we do there.
But your query is not.
I'm saying this in
Order so maybe so really you don't want to look at all. How can you use your whole some other way?
So you're saying
Finding the closest points is only a little bit easier than finding okay. So, like, if you can find the closest one, it's usually not that much harder to find.
Well, see, that's where the.
So the thing is, the hardest part is finding something. It's finding that closest one. Based
Because otherwise we're still like.
Alright, so let's talk about the ideas that we came up with. So, our favorite like searching data structure, order 1 searches, really great. The hash table, is that going to be helpful here? Probably not. Why won't the hash table help us out? Like in order to search a hash table, like what can we use that to find like a range of things? No, hash table, like we have to know exactly what we're searching for, and we can find that exact thing really fast. In this case, we don't know exactly what we're searching for, right? We have no idea which points we're going to return, where they're going to be. We have no idea like the radius that they're going to be in, right? They could be really far away. They could be really close. Who knows, right? So the hash table is probably not going to help us out at all. How else can we speed up searching? So what would the graph? What would like so the nodes would be the points, and what would the edges be? Distances. So would we have? So all of the points are some distance from all the other points. Would we want like all of the edges, or?
I mean, the idea was just like you construct a graph from the array, and then from that point you can figure out.
But we like if we had a graph, potentially there'd be how many edges? Big O it for me. And edges, it's going to be more than that. So in theory, we have every point connected to every other point. And it's not that many.
Two.
Not that many. And so if I have, for each point, so we'll do like the simplified version. For each point, how many edges would come out of it? N, right? So we have n points. So there's n squared edges, right? If I have 1 million nodes in my graph, then that's 1 trillion edges. So that's a lot to store. I could store like just the close by edges, right? So I could have some threshold, store the edges if it's closer than some distance. Yeah. Does that? I don't see how that helps me search faster though, right? It helps me like kind of get around my neighborhood, but it doesn't really help me get to like where I need to start. So even if we did something like that, that might speed up the K part, but it doesn't necessarily speed up the like find the closest point part as far as I can see. Any other ideas?
You could just unfold you could like sort the array and then unfold it into like an array of arrays, or like a 2D structure.
2D structure, okay. So what would like the outer and inner arrays be? So you'd have like an array of an array. So like, what would the index of the outer array mean, and what would like the?
Oh, it would be just like each inside array would be a row, and the outside one would be for each component.
So that would be something like this. Basically, look look like that. Yeah, so this is great, very simple data structure. I just put my points into bins. Okay. When I want to do a query, what do? Find out what bin it's in. Look at all the points in that bin. If I don't get enough neighbors out of that bin, what do I have to do? So look at neighboring bin. And in fact, I probably have to look at the neighboring bins anyway, right? If my point is right here, I'm going to have to look at that bin. But yeah, this is a great data structure. I just I find the bin that I'm in, and then go from there. So pre-processing, what do I have to do? Just put all my points in bins, right? Okay. How do I pick the binning?
Like how big the bins are?
Yeah.
Off the X and Y axis.
But so I'm going to split into X and the Y dimensions. How do I decide like where to split or how many to do? So I could decide ahead of time like how many bins to make. And so I could say in this case I want 5 bins across and 5 bins down. It's great for finding the bin you're in. Yeah. Where would this not be such a great idea? So I'm assuming equally spaced, by the way. So equally spaced works great sometimes, but not always. When would that work really well, and when would it not be so great? Yeah, so if I have regularly spaced data, regularly spaced bins are awesome. Very simple data structure, very fast to find the bin I'm in. It's like a subtraction and a division. Great. If my data is irregular, like say I have a Gaussian, right? The bins kind of by the mean are going to be really full. The bins that are out far are going to be really empty. So how would I search one of these bins, by the way? So I figured out what bin I'm in. How would I find the neighbors within this bin? Probably I just store my points in like an array and then have to like look through each one. Right, so if my bins are really full, then that's going to be slow. Okay. So yeah, the binning is a great technique where one of our data structures is going to be that. We're just going to do a uniform grid bins, and it's a great data structure.
So bins are going to add some inaccuracy unless you take into account neighboring bins, right? So
all of these we are going to be accurate. So we will take that into account. So yeah, we will have to make sure that we look kind of not necessarily just in our bin, but we'll have to spread out a little bit.
how do you know how to do that, I guess?
It's not that hard. We'll take a look at that tomorrow. But, yeah, it's not too hard to add. Okay. So any thoughts on what we could do? Something like this binning technique, but to handle the case where our data is not like evenly distributed. How could we do this binning without getting one really full bin?
They don't have to be the same size, right?
They don't have to be the same size, and so how could I size the bins?
Because every bin has 10 points.
So making them all have the same number of points sounds really hard to me, especially if they have to be rectangular. It's probably impossible if they have to be kind of aligned and rectangular. But I could do kind of something like that, right? So I can just kind of decide where to split based on my data. So we'll talk about a data structure that does that. If I have one bin that gets like really full, what might I do about that? Split it into more bins. So we'll talk about a data structure that does that. Okay. And the other data structure we'll talk about is really clever. It's based on a binary. It's like a binary search tree. But the binary search tree doesn't work great in this 2D example. Why not? Yeah, we have 2 coordinates, right? So there's not really a way to say less than in like a kind of like we can't order the points in a nice way. So the data structure we'll talk about it's like a BST, but it takes into the fact that different coordinates of our data takes them all into account. Okay. And so that's a really clever data structure called a KD tree, and it's like a binary search tree for multidimensional points. So we'll kind of dive into these data structures tomorrow. Maybe if you have a spare minute today, keep thinking about trying to hammer out some of the specifics of how you might do these things, and then we'll talk about the kind of standard solutions tomorrow. Cool. All right. Have a good afternoon.